I proved using basically carriers. The product was signed commutative on the cohomology line by constructing a chain homotopy between the Whitney cup product and the sign flip composed of the Whitney cup product. First thing I want to do today is give you an explicit formula for such a chain homotopy. The argument I gave last week just proved there was one. It didn't just pretty more distinguished one. And of course, the one I'm going to write down is the one that Steenrod originally wrote down in slightly different notation. Oh my God, 7 years ago. 65. So remember from last time we have the Whitney formula, which we view as a map from the singular chains of X to the tensor product of the singular chains of X with itself.
Could you please use the chart in the box?
Yeah.
In the black box. Well, one of the black box.
Okay. And it's a chain map, so it's a degree 0 map. That is to say, it takes something in degree k here to something here of total degree k. And it's a chain map. So, boundary composed with Whitney would be the boundary, sorry, that would be the boundary here, which is the tensor product of the boundary on this factor, and up to a sign the boundary on that factor is Whitney composed with boundary. And their definition of cup product was alpha cup beta, as if these are cochains, the cochain alpha cup beta on a simplex sigma is simply alpha tensor beta evaluated on this Whitney map applied to sigma. And I just remind you that the Whitney map of sigma is the sum over k of the front divisions of sigma tensor minus k face of sigma. Okay, so this gives you the usual Whitney formula. This is a k and n minus k. You get alpha on the front k face and beta on the back n minus k face. So our chain homotopy is a map H1 from the singular chains on X into the singular chains on X tensor itself. It's not a chain map. First of all, it doesn't preserve degree. It's a degree plus 1. Meaning it's in something of degree k here, something of total degree k plus 1 here. And the formula for involving the boundary of this H is that this is T composed with Whitney minus Whitney. This being the signed flipper factors. Okay. So this is one of the places that can be a chain map. And in fact, it's convenient here to relabel Whitney as H naught. So this equation becomes an equation linking H naught, a degree 0 map, the Whitney map, with H1, this first chain homotopy. Okay. So I'm going to give you the formula by giving you pictures. So the picture for H naught, or Whitney, is this. And so associated to an n-simplex, you look at all pictures like this, where k is going to be free to run from 0 to n. And that's in fact H naught of the simplex sigma is the sum over k. Let's call this diagram P, K, semicolon, n. So k refers to where you drop from the first row to the second, and n refers to the total number, well, the dimension of the simplex is being represented there. So it's the sum over k of a tensor, well, an element in the tensor product that I'm going to label the same way I label the diagram. So there'll be some signs here. Well, no, the signs here are all plus 1. It's just going to be the sum over these diagrams, maybe I'll put an underline under it, to indicate this is an element in the tensor product that's described by this diagram. And the rule for going from diagrams to elements in the tensor product, so P bar A N is the tensor product of A tensor B, where these are determined by the diagram. A is simply the simplex restricted to the vertices, the span of the vertices 0 to k, the vertices in the first row, and B is the restriction sigma to the vertices in the second row. Okay. And we're going to have lots and lots of diagrams in a minute, by the end of the day. All the diagrams are going to have 2 rows. And when I pass from a diagram to an element in the tensor product, it's always an elementary tensor. It's an A tensor B, where A is the face that has all the vertices in the first row, and B is the face that has all the vertices in the second row. So this is a general paradigm to go from pictures to elements in the tensor product. Okay. So for example, we're going to, in just a minute, see a diagram like this. So we call this diagram P, K, L, N. K and L being the breakpoints, and N being the simplex we're talking about. And then the element in the tensor product, P bar, K, L, N, underline, would simply be the tensor product of sigma restricted to the face with vertices 0 up to K and L up to N. And so the restriction of sigma to the face with vertices K up to L. Okay. So it's an elementary tensor in the, and it's simply a tensor product of sigma on some face, tensor sigma on some other face. And if you think about it for a moment, you'll notice that the degree of this thing is, well, what is the degree of this thing?
N plus 1.
I heard somebody say it.
Yeah, N plus 1.
And why is that? Okay. The one way to think about it is let's count the total number of vertices we see here. Okay. So we see every vertex from 0 to n, that's n plus 1. But then we see 2 of them repeated. So we have n plus 3 vertices, and they're supposed to make 2 simplices out of n plus 3 vertices. Well, a simplex with k vertices has dimension k minus 1. So we dropped 2 in the total dimension to get the total dimension. So it's n plus 3 minus 1 minus 1. There are other ways to do it, but that's a way to keep track. And so you see this diagram had 1 repeated vertex and was of degree 0. This diagram has 2 repeated vertices and is of degree 1. And you can probably figure out if I have a diagram with r repeated vertices, it will be a degree r minus 1. Okay. All right. So, in fact, H1 is defined by the H1 diagrams are exactly the ones I was just drawing. They're the P, K, L, N. And of course, you have to define H1, you have to let, of course, N vary over all non-negative integers. And K and L are required to be 0 less than or equal to K, strictly less than L, less than or equal to N. Those are the conditions. And this diagram is the one I drew over there. 0 to K, L, N, K, L. And there is a sign, epsilon K, L, N, sign. I'm not going to say much about the signs, it'll come up a little bit. And I'm essentially going to work mod 2 so that signs don't matter today. But I just want you to know that you can work over the integers and there are signs, and occasionally I'll say something about it. The sign that goes with this diagram, you'll see after I write the sign down why I'm not going to keep track of them. The sign is, this thing is minus 1 to the power, where'd it go? NK plus NL plus KL plus K plus L plus 1. And then H1 of the simplex sigma is simply, well, let's say delta N is simply the sum of these signs plus minus 1 times the tensor product element that's associated to the diagram. In other words, the face of delta N with these vertices tensor the face of delta N with these vertices. And once you have, as before, once you have H1 on delta N, you define H1 on an N simplex to simply be sigma star tensor sigma star, the map induced on singular chains of H1. This is an element of the tensor product of the singular chain of delta N with the singular chains of delta N. You just push forward both factors, just like we did before. Okay. So this is the explicit definition of H1. And now my claim is this explicit definition satisfies this formula.
So what is sigma? So sigma star tensor sigma star is acting on the sum of the pictures, or is that time?
No, it's better turn on my phone.
Yeah, that was me actually, sorry.
No, H1 of delta n is in the singular complex of delta n tensor the singular complex of delta n. Okay? Now sigma is a map from delta n into x. So I can, given any singular simplex in delta n, I can follow it by sigma and get a singular simplex in x. That's what sigma star means. So it's on each factor, you simply oppose with sigma into the singular, well, singular x tensor singular x. That's all. Now I'm just, it's the same, I mean, this is the picture for delta n. If you want to know what's the picture for, what do you do for sigma? You take the same picture and you simply restrict sigma to this face, tensor the restriction of sigma to that face. Whereas for delta n, delta n has these as vertices, so this naturally represents a face of delta n as does this. And if you want to apply to sigma, then you have to push forward by sigma. All right, well, I'm going to prove this by pictures. And I'm not going to worry about signs, so it's a mod 2 proof, but if you're interested, you can follow the signs through and get the signs I gave you. It's already massive, so you can see. Yeah.
Just to clarify, the formula that you just raised, which defined P double underscore as sigma restricted to that set of vertices, that would work just as well as singular chains into the space X as opposed to delta N. We could define it without reference to
Yeah,
X.
when I wrote that formula down, I was thinking inside the singular complex of X, right?
So in the same way, if we just replace delta N there in that line with X, then
And you just
the
have to
notation-
implicitly have a sigma
Okay.
hidden, or made explicit if you want. Okay. So let's think about the boundary of H1 of delta n. Now again, I'm going to work in the simplex, but in fact, once you do these arguments in the simplex, they'll follow by naturality in any space by just applying sigma as you need. So all the computations are done in delta n. So here's a diagram. So I'm supposed to sum over these diagrams. This is P, K, L, N, and I'm supposed to look at the sum with signs, which I'm going to ignore now, of the associated tensor product of, well, the element of the tensor product. Okay. So let's think about what happens when we try to take the boundary of the part of this thing associated to one of the diagrams. And then I'll sum up over all the diagrams. Well, I claim that the boundary of this thing is simply, there's signs here which I'm not going to write down. It's work mod 2. It's the sum over all diagrams derived from the original diagram. Well, some of them are not all diagrams, but all elements in the tensor product. Deduced from all diagrams derived from the the original diagram by deleting a vertex, a single vertex. Well, that was a complicated statement. Pictures are worth 1,000 words. So what can you do? Here's a diagram. K, L, M, A. One thing I could do is I could just remove the vertex I, just skip I. Or I could remove a vertex. So here I is less than K. Here I could remove a vertex J strictly between K and L. Or the other thing I could do, the same vein, is drop out an I, which is, actually, drop out an I, which is strictly bigger than L and less than or equal to N. Those are things I could do, but there's other things I could do. So this is one class of boundaries. We'll call these type 1 boundaries. But there's another type. Let me just look out here. The other thing I could do is I could leave out one of these, one of the copies of the repeated vertex. So there are 4 possibilities here. I could leave out this one. I could leave out this one. I could leave out this one, or I could leave out this one. So I try to indicate that when I'm missing a vertex, I don't draw a strong, complete vertical line because it's not connecting 2 vertices. But the circle tells you what vertex has been deleted. And that's it. If you're going to delete a vertex, you either have to delete one of the ones that's not repeated, and that's all the possibilities there, or you have to go to a repeated vertex and drop out one of the 2 examples of that vertex. And it should be clear to you that, again, ignoring signs, this is the boundary of this diagram. So I'll now sum up over all diagrams, all K and L, all ways to delete a vertex. And that is this. So we'll call these type 2 boundaries. Okay? Well, now let's think about H1 O's boundary, do it in the other order. So now I take the simplex and I drop out a vertex and then I do this splitting. What will I get in terms of these diagrams? Which of these are going to occur?
Those belong.
So certainly these don't occur because they include all vertices. But in taking the boundary, the first thing you do is drop out a vertex. So all of these will have to be diagrams of this type. Which of this type occur? Speak up.
All of them?
All of them. Because you drop out a vertex and then you take all possible diagrams that have this shape but don't include that vertex. Well, I've got them all here. Now, the labeling would be different. I call this K and L, but actually it comes from the boundary I, where this is k minus 1 and this is L minus 1, because of the way the face is included. But that doesn't matter. That's implicit in these diagrams. I mean, when you take the diagram with k minus 1, L minus 1, and you include it as the I face, you shift over the k minus, you shift over this part of the diagram by 1 because you skipped that vertex. And you will get exactly this diagram. So this is all type 1 diagram. So if I'm adding up boundary H1 plus H1 boundary, and remember I'm working by 2, this is all type 2 boundary diagram. So this is what we're left to analyze. And what I'm going to claim is, well, there's a lot of these. They're going to cancel out in pairs, except for the extremal cases, which give you Whitney and the flip of Whitney. Okay.
Wait, sorry. Explain why again. H1 composed with boundary only has, it has, why doesn't it have type 2 boundaries?
It does. Sorry, why doesn't this?
No, why doesn't the one above, H1?
Oh, because the process is you first take the boundary of the simplex. That means you look at, take a boundary of the simplex. You look at one of the faces. You're looking at the I face. When I include that boundary, that face in the entire simplex, I get the face that does not include the vertex I. Now I do my division in diagrams. Well, I'm never going to put a vertex back in that's not there. So the diagrams will not have the vertex I in them. But all these diagrams have all the vertices in them. Every vertex appears somewhere in this diagram. Whereas over here, there's definitely a vertex that does not appear. And a unique one and a unique way to get it from the I space. So these both have boundary 1 diagrams, and if you're careful about signs, you'll see the signs cancel, so you're left with the boundary 2 diagrams. All right.
And do we believe that all? So the claim was initially that when we analyzed this, every single diagram would appear exactly what's.
That's right.
Okay.
Yeah, I mean it appears, right, these coefficients are all 1, plus or minus. For me now, they're all 1. So I just have to count how many times the diagram appears. And, yeah, okay. So let's think about the telescoping cancellation. Let's start with k plus 1, 0, n, and suppose we've deleted this vertex. There's another way to get exactly the same, not diagram, but same set of vertices here. By the way, this is 0. I realized my 0 and my removals seem a lot alike. I realized when I was looking at what I've done. Anyway, there's another way, another diagram that has the same set of vertices here and here. Namely, k plus 1, k minus 1. So this is the diagram we start with. Okay? And we delete this vertex. So let's just check. What vertices do we have on the top row? Well, we have 0 to k minus 1 and k plus 1 to n. Well, what vertices do we have here? 0, we don't have k, so it's 0 to k minus 1, k plus 1 to n. So the vertices on the top row are the same. Vertices on the bottom row, well, here we have k and k plus 1, and here we have k and k plus 1. So those two diagrams give the same answer, even though they don't look like the same diagrams, because they have the same set of vertices on the first row and on the second row. Okay? So I'm going to do a telescoping argument to the left here. I'm going to start here with this deleted vertex, and now see what cancels that. But now let's take this one out and ask what cancels that. Well, you move one more step to the left. And so you cancel these diagrams. One missing here cancels the one missing here, the one missing here cancels here, all the way down until you get the one missing here cancels the one missing there. But there's nothing that will cancel this one when you drop this guy out. Follow me?
Yeah.
So what's left over? What's left over, we had the diagram, well, we were doing shorter and shorter diagrams, but always ending in k plus 1, and then going up to n. So these diagrams, this part of the diagram is staying the same, and this part is moving back to the left. And so the last diagram you get is when this is 0. And you delete it.
The operator.
No.
Do you want to draw the circle at the bottom for the second diagram?
Well, as I'm moving to the left, I cancel this circle with the bottom circle at k minus 1, and then I cancel the top circle at k minus 1 with the bottom circle at k minus 2. And I can continue to do that until I use top circle 1 and bottom circle 0.
Yes.
So
So
you want
that
to delete-
diagram is actually at k minus
Yeah, I said
1.
that diagram is canceled, and I'm left then with,
You take away 0 from the top.
More specifically on the board, on the left side of this, you have two diagrams. I claim that on the lower one, you should have a circle on the bottom or on the top.
yes, you're right. I need colors. That's the cancellation. No.
No.
Red.
The next one on the left upstairs should be red.
Yes. Red. Red. Right. Yeah, so I keep going, and I'm left with
The cancellation on the top.
this diagram and delete this guy. And what do I get?
Oh, so H0. Sorry.
I get T of H0,
Oh.
because it's the bottom rather than,
Oh.
it starts at the bottom. Now, I haven't sorted out the signs, but we're not worrying about signs. Okay, so this produces a T of H0 split at K plus 1. That's the remaining term when you do this telescoping to the left. Now let's do telescoping to the right. So let's again take the same diagram that we started with, split at k and k plus 1, the verticals at k and k plus 1, and this time let's telescope canceling to the right. Okay, so this one, did I get that one? No. This one, now, will cancel. Sorry, it's this one. This one will cancel with this one. So now I'm going to the right. This one cancels with this one. And I keep going. And the last cancellation I can do is when I'm at n minus 1 and I cancel with n, and then I'm left with this one which has no partner to cancel. There's nothing out here can cancel. And that's the diagram k all the way to n, and you drop this one out.
Oh,
Okay.
this is H0.
So that's Whitney. That's Whitney at k. So that's split at k. Okay? So that's pretty good. But I haven't accounted for all the diagrams yet,
Yeah.
because I have these two that I haven't talked about. Okay? I started here and moved to the left, and I started here and moved to the right. I never used either one of these. I never dropped out either one of these. Okay? So let's think about what happened there. So that leads to something I call a degenerate diagram. So here's k and k plus 1. Suppose we drop out of this vertex.
It's the same as.
That leads to a diagram I would draw like this. So the top has all the vertices, and the bottom now only has one vertex. And this diagram, I call it degenerate because it doesn't have the structure of any of the diagrams that I'm interested in. What happens if you drop out this one? So this gives that. This gives k. Because once again, the top has all the vertices, and the bottom has only k. Well, now it's clear, right? These cancel out in the telescoping fashion as you shift where this drop is. If you shift it over 1, you'll have k and k minus 1. And you'll keep going. So you get a telescoping collapse of all of these diagrams, except they're two extremal ones. Right? So these cancel in a telescoping fashion, except for you're left with these two. What are those?
The extremal of H0.
They're the extremals of H0.
And
With-
H0.
This is where it's a vertex times the whole simplex, and this is where it's the whole simplex times a vertex. And you just have to think for a second to see that the Whitney diagrams you get here are never extremal. It was clear one way. I said the split was at k plus 1, but I can't be split at 0. You just have to think that k could have been the first one even. So what we're left with is these extremal things either ordinary extremal or degenerate extremal, which give among them all the Whitney diagrams, each one counted one. So that's the proof. When I first sorted this out, I didn't do it by diagram. I did it by formulas, you can imagine.
Did he draw these pictures?
Huh? No, Steenrod wrote down formulas.
Oh, no.
These pictures are the leading edge of the operatic view of all of this. There's things called step operats, of which this is the two-step operad. There's an in-step operad for every in.
It's not just a combinatorial trick.
I guess it's combinatorial. I don't know how Steenrod came up with these formulas. But
You believe H1 exists and you start from lower dimensional and then you figure
yeah,
out.
maybe some argument by analogy. Okay.
How did we improve this homotopy formula last time?
I proved it last time by, there was no formula to prove, I just proved there was an element. You go by induction, and you're trying to solve this equation. So delta n. Okay, and the argument I gave was, I've rewritten it, I brought this term to the other side. Okay. You check by an inductive hypothesis, induction on n, that this thing's closed. But you're working in the singular complex of the simplex tensor itself, and that's acyclic. So anything that's closed is exact. So there is an H1 that solves this equation. No formula.
I think Steenrod was probably motivated by the picture of like a prism as a chain homotopy between the bottom and the top, where you just duplicate vertices.
Yeah, well, if you take this prism, for example, this is the Whitney formula, and here's its opposite, and it's sort of clear that there's a homotopy across here. Maybe, I don't know. Anyway, that's H1. But in fact, this is just the beginning of a whole collection of higher chain homotopies. So the claim is all k greater than equal to 0, there exists hk, mapping the singular chain complex of x into the tensor product of degree k. So element of degree r here goes to something of total degree r plus k, satisfying one, h naught is the Whitney, 2, boundary hk plus minus 1 to the k, minus 1 to the k, hk opposed to boundary is flip applied to hk minus 1 minus 1 to the k minus 1, hk minus 1. So these are higher chain homotopies.
What do they mean?
Well, we're gonna get to that.
Wait, is that another, the two boundaries?
No, that's a mistake. So if you plug in k equals 1, this reads boundary H1 plus H1 boundary is the flip of Whitney minus Whitney. So the special case k equals 1 is the formula we already have. Okay. Well, let me say a word about where these come from. It's the same idea that we just did for H1. I'm not going to prove in detail that it works. But then I'll try to answer your question, what does it all mean? Because nice answers to that. Well, you probably can guess. So I'm going to follow the second track, the one I've introduced today, and give you explicit formula for the HK. So let's look at diagrams. P of A0, A1, up to AK, and N. So it's a diagram like this. A0, A0. I won't repeat, the vertical lines are really vertical. Now, depending on whether K is even or odd, this diagram always starts on the first row, and it may end in the second row or the first row, depending. When K is even, it ends at the second row. When K is odd, it ends at the first row. Okay. And the condition, of course, is that 0 is less than or equal to A0 is strictly less than A1, and so on, up to AK, which has to be less than or equal to N. Those are the diagrams that I consider. For each diagram, I get an element. In just as before. Use these vertices for the first factor, these for the second. And to define HK of delta N is a sum over all diagrams, like this, of the sum times this thing. Times the tensor element, tensor product associated to the diagram. Okay. Exactly what we did before. I don't think I'll say much about these signs. This is a sign. Plus minus 1. And the claim is you have this formula. Let me just say briefly how the argument goes. Again, when you look at this term, you take all diagrams and all ways to delete one vertex. Again, they divide those boundary diagrams divide into two types. Those where the deleted vertex is not repeated, and those where it is repeated. the diagrams where you drop out an unrepeated vertex are what give you this. So once again, you're left to study the diagrams where you dropped out one of the two examples of a repeated vertex. And there is a telescoping collapsing. You get some degenerate diagrams, you get non-degenerate diagrams, they all telescope. You're left only with the extremal ones, which, just as before, drop you down to HK minus 1. Well, to be fair, it's a little more complicated, but the basic principles and the basic argument are the same. Just more complicated. But it all works. I put the signs in the notes, so if you're interested, you can read them. All right, I want to do a little more combinatorics before I tell you what it means. So using this, Steenrod defined the cup I products, generalizations of the cup products. So if you start with two singular cochains of, let's say, between P and Q, you can form their cup I product, which is denoted this way. And it's of degree, it's a cochain of degree P plus Q minus I. Maybe let's call it K to fit with. Though they are called the cup I products, can't help that. And what you do is you take, it's by definition, it's alpha tensor beta in the tensor product, evaluated on HK of sigma. The value of this cochain on a sigma, which will be of degree P plus Q minus K, is this tensor product, which is of degree P plus Q, evaluated on HK of this P plus Q minus K simplex. That'll also be an element of total degree P plus Q. If you take K equal to 0, you get the usual cup product. Now this formula, it's a nice exercise. This formula, ignoring all the signs, I'm going to work my 2 here, shows you that the co-boundary of alpha cup K beta, okay, is co-boundary of alpha cup K beta plus alpha cup K co-boundary of beta. That's what you get for the usual Whitney product. And that's what this gives you. But now there are 2 more terms, which are alpha cup K minus 1 beta plus beta cup K minus 1 alpha. And they come from these 2 guys. The T switches alpha and beta, so this term is going to give you, these 2 terms give you these 2.
Are we working mod 2 here?
Yeah, this is all mod 2. There are formulas over the integers with signs, but I'm not trying to write them down.
Wait, so if you flip the 2 factors, show the sign is -1 to the something.
PQ. Well, here I'm working on 2.
Okay.
Yeah, so for example, there'd be a sign in front of this term.
Those last 2 terms vanish. Like,
No. Because think about K equals 1. K equals 1 says the co-boundary of alpha cup 1 beta. Now these are, I'm going to take these to be cocycles. Now look at this formula for cup 1 in the space, in the special case of 2 cocycles. What does it give me? Well, again, I haven't worked out the signs. These two vanish because alpha and beta are cocycles, and I'm left with alpha cup naught beta plus beta cup naught alpha. That's the commutativity of the cup product. Now, if I worked over the integers, it would turn out this sign is a minus, or minus 1 to the PQ. So I guess that's sign. And therefore, this is the usual skew commutativity of cup product. It's realized by this cup 1. The co-boundary of the cup 1 is what realizes the fact that the cup product is not graded commutative on the nose for cocycles. So these higher terms, well, I won't say more about that. So those are the cup I. That's one thing Steenrod did with all this machinery. The other thing he did with all this machinery was to find these Steenrod squares.
Sorry, what was the remark about signs?
This formula is a mod 2 formula, so there are no signs in this formula.
Some might be minus, but you don't want to get into it.
Well, this has got to be minus 1 to the PQ, I guess. And then I said, okay, if you look at this formula mod 2 and apply it to Z2 cocycles, you see that the co-boundary of this thing shows you the cup product is commutative in cohomology because it compares alpha cup beta and beta cup alpha. If I wanted the right sign over the integers, I would need a minus 1 to the PQ here.
There exists a non-mod 2 formula though.
Sorry?
There exists a non-mod 2 formula.
There exists a
Integral formula.
non-natural?
Integral. So it is possible
Non-mod
to
2.
put signs that this way.
Yes, there exists a non-mod 2. Yes, these signs that I didn't tell you what they were are enough to make these formulas that I wrote down here with signs hold. And as I tried to indicate, this formula is deduced from that one by just plugging in. And so the signs you have over there will produce signs here. I just haven't tried to work them out.
Does the definition depend on the choice of H1 and H2?
Does the definition? Yes, the cup I at this cochain, certainly. The definition of this on the level of cochains absolutely depends on the choice of H1. And you choose a different H1, you get a different cup 1. But it still satisfies the same formula. Okay, Steenrod squares. Suppose that alpha, and I'm still working now, I'm really working line 2. I have to work line 2 for this. So, singular Z2 cocycle. And alpha tensor alpha is an element in the dual cochains associated with the tensor product of the singular chains with itself, given an element in tensor into Z2. Given an element in tensor product, you simply evaluate alpha on the first factor, evaluate alpha on the second factor, and multiply by 2. Okay. Now, this is a cocycle. Alpha tensor alpha is a cocycle because of the boundary formula. Boundary alpha tensor alpha plus alpha tensor boundary alpha. The cocycle, and it is invariant under Z2 action flipping the factors. The involution on x cross x are here on the same tensor set. I don't have to worry about this sign because I'm working on it too. So it's just. So that's an equivariant cocycle, and it determines an element in equivariant Z2 cohomology. So it's a cohomology class of alpha tensor alpha in, well, it's a 2p-dimensional class, and it's equivariant. This is equivariant cohomology of x cross x. Those are the two coefficients. Large, long, singular complex. What? No, I'm sorry, I'm mixing my stories here. Let's not do it that way. Let's just take alpha cup K alpha. And let's take the coboundary of that. Well, it's coboundary alpha cup K alpha plus alpha cup K coboundary alpha plus alpha cup K minus 1 alpha plus alpha cup K minus 1 alpha. These are the same, and alpha is a cocycle, so everything vanishes. Okay. So this is a cocycle. If we vary alpha by a coboundary, and take the cup 1, well, sorry, yeah, and take cup 1, yeah.
The alpha plus delta beta.
Yeah. So, I start with a cocycle alpha, and this produces an equivariant cocycle. I want to show if I vary alpha by a coboundary, I vary the resulting cocycle by a coboundary. So I guess I want to take cup K of this. By bilinearity, I'll get alpha cup K alpha plus alpha cup K beta, beta plus coboundary beta cup K alpha plus coboundary beta cup K coboundary beta. Right?
Yep.
I want to claim this is a coboundary. So let's take the coboundary of alpha cup K minus 1 beta. Let's see what we get. No, K minus 1 coboundary beta.
Plus 1?
Minus 1. Plus 1, you're right. 1 degree lower. So I get 4 terms. I can take coboundary alpha, which is 0. I can apply the coboundary to coboundary beta, which is 0. And the other 2 I'm left with are alpha cup K coboundary beta plus coboundary beta cup K alpha. So this thing gets those 2. Now I have to worry about this. What should I do with that?
Beta cup delta
Beta cup K coboundary beta. Is that what you said? That looks good. Let's take the coboundary of that. Well, you can apply the coboundary here. It gives me what I want. You can apply it here. It gives me 0. Beta cup K minus 1 coboundary beta plus coboundary beta cup K minus 1 beta. And this, I do just put it over here. And so this is coboundary of beta cup K minus 1. That doesn't seem right.
correct, yeah.
Hmm?
Yeah,
It's okay?
good,
Like a co-boundary beta, was K minus 1.
Yeah.
Co-boundary beta, 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 co-boundary beta, that's those two.
Beta, beta,
And
beta,
then beta, 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 beta. They cancel. All right, so all of this is a co-boundary. So alpha, if alpha is a cocycle, this is a cocycle, and its cohomology class and cohomology class only depends on the cohomology class of alpha. So this cohomology class in H2P minus K of X, Z2 coefficients, depends only on class of alpha in HP of X. And this is the definition of the Steenrod square P minus K of alpha. Yeah, P minus K. So square raises dimension. We started with something of dimension P. This raises dimension by P minus K. We end up with something of dimension P minus K. That's 2P minus K. Now, the square of alpha, the squares of alpha will vanish above P. So the biggest square you can apply to the class of degree P is square P, and that's the usual cut product. Square naught is the identity, which you can check.
Do you mean x cross x there?
Yeah, sorry, say again?
That space should be x cross x, right?
No. No, this is all in X.
The couplet that lives in the
one above.
in the tensor.
The one above.
A cup K, A.
So you need to go back by the
It's
dimension.
definition X.
Cup K goes from the cochains on X to the cochains on X. Takes,
Just raises degree though.
sorry?
Okay.
If you have two classes, then you're starting, I guess, you're starting with two cocycles in X and ending up with one. Here I'm starting with one cocycle and ending up with a cocycle. So these Steenrod operations are natural cohomology operations. And this is natural for continuous maps or even the homotopy classes of maps. So you have a continuous map from X to Y, the cohomology class in Y, and you take some square of it, you pull that square back to X, you get it by pulling the original class back and taking the same square. So these are natural transformations between the functor Pth cohomology and 2P minus Kth cohomology on the homotopy category. Now I want to turn to Tony's question. What does it all mean? Okay. Cohomological reinterpretation of all of this. And we begin with the projective, or in fact, the usual free resolution of Z as a Z of Z2 modular. Well, this Z has two structures as a Z of Z2 module. So this is just an integral group ring. And it depends how the element and non-trivial element in the group acts on Z. To make an abelian group a module over a group ring, you just have to say how the group acts on the abelian group, and it has to be a abelian group automorphism. So I need an involution of Z. Well, there are two of them, +1 and -1. This is the +1. So this is the trivial module. Okay? So I want a free resolution. And in fact, free resolution is, going to look familiar, this is just the augmentation. given a sum of integers times group elements, you just add up the integers. And this is t minus 1, and this is t plus 1. Alternating between t minus 1 and t plus 1. So if you put, this is the change in degree 0, this is the change in degree 1, this is the change in degree 2, and so on. And this map is 1 minus t, 1 plus t.
What is T?
What is what?
T.
T is the generator of Z2. So Z2 is 1 t squared. So I might write this, starting in degree n, I might say t minus 1 to the n 1, to make it look like the formulas we have right here. So this is the standard free resolution of Z as a Z of Z2 module. But of course, there's a much better way to think about this if you're picture oriented, which is take the infinite sphere with all its equators. So that's not inside x1, inside x2, and then you take the inductive limit with the weak topology of the SNs and inclusions, and you call that S infinity. It is, of course, the unit sphere in R infinity, vector plus 1. So take R infinity, the weak limit of the vector spaces Rn, take summation xi squared equals 1, but you're only allowing finitely many of the x's to be non-zero, but any finite number, and then that defines the unit sphere. Well, this is a CW complex. And the natural way to give it a CW structure is with 2 cells in each degree. So you start with S naught, and you have 1 and minus 1. And then I will call this E naught plus and E naught minus. And then we have 1 cell, E1 plus, and the boundary of E1 plus is E naught minus E naught minus minus E naught plus. And then we have E1 minus, and then we have E2, the upper hemisphere, and that's E2 plus. We have E2 minus, the lower hemisphere. So En plus is the upper hemisphere of Sn minus Sn minus 1, and En minus is the lower hemisphere. Okay, so there's our cell decomposition. There's a natural action of Z2 acts topologically on the sphere. It's the antipodal map, and it preserves its cell structure. It's in cells to cells. Acts on the CW, on this CW complex. And of course, it interchanges the 2 cells in any given degree. It sends En plus to En minus, and En minus might be En plus. And as I've already said, the boundary of En plus is En minus 1 minus, minus minus 1 to the N, En minus 1 plus. Well, that's exactly what you have here. If you think of the CW chains on this space, you will have a free beginning group of rank 2 in each degree, 1 for the upper cell, 1 for the lower cell, but they have a Z2 action which reverses them. So in fact, you should think of those chains as free Z of Z2 modules of rank 1. Now, you have to choose a basis. You have to say, well, you're going to use the upper hemisphere or the lower hemisphere as your basis. But if we always use the upper hemisphere, that gives an isomorphism between the CW chains and this projective resolution, this free resolution, and these are the boundary maps. So this picture of the cell complex is a picture of this resolution. And not surprisingly, if you take the quotient of this S infinity by Z2, by the antipodal map, you get RP infinity, which is the classifying space for this group. It's the K pi 1 with pi Z2. I mean, anytime you have a contractible space and a free action of a group, the quotient is a K pi 1, but we're realizing this is a CW complex with an action, so we're actually getting projective resolution to free resolution of the integers. So that's S infinity, has a Z2 space and its CW chains. And I'm going to call those chains C star. So C star, the CW chains with respect to this decomposition of S infinity. Okay. And then give me that resolution. Okay, so now I'm going to use these H's, these HKs, to define a map, chain map, from C star, since there's a singular complex of X, into the singular complex of X, tensor the singular complex of X. Here, both domain and range of this map are modules over Z of Z2. Here, I take the module structure I've already talked about on the sphere, tensor the trivial action here. And here, Z2 acts by flipping the factors with a sign. So I have two Z of Z2 chain complexes. Chain complexes modules over Z of Z2. Okay. I'm going to define a map here. It's going to send EK plus tensor sigma. Sigma is a singular chain. So that singular simplex is going to go to HK of sigma. Okay. So the first thing to notice is that this is degree preserving. This is, if sigma is an n simplex, this is something of degree, total degree n plus k. Sigma is an n simplex, this raises degree by k, so this is also degree n plus k. So it's degree preserving. Now, that's not a map on the whole chain complex because this is only half of the cells here. On the other hand, I want it to be equivariant under Z2, so that gives me no choice about what to do. EK minus tensor sigma goes to T pose EK sigma. T is the involution here, is generating the Z2 structure. So I'm just forcing T of this guy is this, and the generator acting here, it acts trivially on sigma, so it sends E plus to E minus. I want this to be equivariant, so I better send this to its image under the involution. So this is an equivariant map. Or another way to say it is a Z of Z mod 2 module homomorphism. Okay. And what do those formulas say? What do you think those formulas say?
What formula?
Sorry?
What formula?
This formula.
What do you mean by equivariance?
That if you act by the involution, you take something here, you could push it over and act by the involution, or you could act by the involution and push that guy over. They're the same. That's what equivariance. That's what equivariance always means when you have free action. the formula, this formula. What do you think this formula says?
The form.
Quasi-isomorphism.
Chain map. Well, I've got an equivariant map between chain complexes. What's the first thing I'd like to know?
Is it a chain map? That's what that formula says.
Huh? Oh. Yes.
Equivariant chain map. I mean, when you take the boundary of something here, you have two pieces, right? One is what happens to the boundary of EK, that's this. And the other is what happens to the boundary of sigma, and that's that. So the boundary of HK, anyway, it's a straightforward exercise. All right, so we have an equivariant chain map. So we have this map. I like to think in terms of spaces rather than chain complexes. And we don't really have we could define a map like this. That's Z2 equivariant, flip of factors, acting over here. I can have a continuous equivariant map here. This is a chain complex model for that map. And it's equivariant in the chain complex where you're flipping factors. So such an equivariant map produces map on cohomology, on equivariant cohomology. Now here, we're in pretty good shape because the action here is free. Because it's free on the S infinity. Free. No fixed points. No element has fixed points. Except for the element.
What does the subscripts and the coefficient mean both present?
Okay, so this is the coefficients I'm using for cohomology. So I'm taking homomorphisms of the chain complex to Z2. This is a different Z2. This is the group that's acting. And this is my sign symbol for equivariant cohomology. So if X has a finite group, or sorry, discrete group acting, then you talk about the equivariant cohomology of X. I haven't yet defined it.
It is standard to make these two, have these two notations for Z2 in the same formula.
Well, that's just unfortunate. In fact, you have a map like this. Again, these signs really work, so this is defined in the integers. However, okay, and this, because the action here is free, this is just the ordinary cohomology of the quotient by the group action, which in this case is RP infinity cross factor. Let me leave out the coefficients, because I'm going to switch it in. Okay. So far everything works with all coefficients. But things become very nice when I take Z2 coefficients, because the Z2 cohomology of RP infinity is polynomial algebra. So with Z2 coefficients, this is simply a polynomial algebra over Z of Z2. So that's the ground ring with one polynomial variable in degree 1. That's the cohomology of RP infinity, and then I have the tensor with the cohomology of X. So the upshot of all of this is that I have a map these chain homotopies give me a map from the equivariant cohomology of X cross X with Z2 coefficients into the tensor product of Z of Z2 polynomial ring over Z of Z2 with one generator in degree 1, tensor the cohomology of X.
Is it Z mod to X, not Z?
Sorry?
Each star RP infinity is Z mod to X. Not Z mod to X.
Right. Thank you. Yeah. Yeah, so the ground ring is the vector space, 2 elements, and this is the polynomial ring algebra. Thank you. Okay, so now we can take our alpha cocycle and act. And I can take alpha tensor alpha. This is an equivariant cocycle on X cross X. Equivariant with respect to the involution, the flip of factors. So it determines a cohomology class in equivariant cohomology of degree 2p. So I push it forward and pull it back under this map, the map given by all these chain homotopies, and I get something which is a polynomial in X with coefficients in the cohomology polynomial, let's call this T. Polynomial in T with coefficients which are cohomology classes in X. So this is a summation of T to the R, and some, let's call it Steenrod 2p minus R of alpha. So this is some cohomology class in X, completely determined by alpha. So the same arguments I gave you before shows that this equivariant cohomology class only depends, this is a equivariant cocycle, and its cohomology class in equivariant cohomology only depends on the cohomology class of alpha. So these things only depend on the cohomology class of alpha, and they're new cohomology classes in degree 2p minus R. So I have the Steenrod 2p minus, actually, for strange reasons, the terminology is p minus R.
Oh no.
Of alpha in H 2p minus R of X with Z2 coefficients, and they depend only on the cohomology class of alpha in H2 of X. Okay. Well, the relationship to the Steenrod squares is the square R of alpha in Steenrod p minus R of alpha. It's another way of say what the Steenrod squares do. You take this cocycle alpha, you square it in this sense. You take its equivariant cohomology class, you pull it back by this huge infinite dimensional chain homotopy, which works on S infinity cross X. The cohomology there is simply a polynomial algebra of these coefficients. And you just read off the coefficients. And those are the Steenrod squares with an appropriate shift in the C. Steenrod, yeah.
Did Steenrod do this also?
Yeah, he actually defined these. It took him a while to realize it was more natural to take the squares. These were the first things he defined. But I think I've got my idea. So this is degree R. So this should be degree
2p minus r.
2p minus R.
Degree value.
So maybe I call this R. And then, because there's a flip here. P minus R.
Is there a standard notation for this?
Can I do what?
Is there a standard notation for this?
Yeah. So certainly the Steenrod squares, that's what you see. The Steenrod square SQ raises degree by Q. These disappeared.
Oh.
They're not as, I mean, they're equivalent, but it's more convenient to think in this language. But I believe I've got Steenrod's original notation correct. All right, well, I did all this formula. I will leave it to you as an exercise to show that you can prove using acyclic carriers the same thing, but without, of course, producing particular HKs. And the argument is the same. You look at, you go by induction, you assume the previous HK are defined, and the HK minus 1 and lower are defined, and that HK is defined on the simplices of dimension less than n, and you look at this expression and you show it's closed, which requires some iterative arguments that are so nice. And thus, there is an HK on the n simplex that solves this equation, again, by acyclic carriers. In some sense, it's the same argument. But you have to work a little more because the formula got these extra terms in it now and iteratively how it all works. So you can do it that way as well. Many people prefer that way. I'm quite fond of these formulas, but
Is there an advantage to doing it acyclically?
well, there's certainly an advantage in understanding how acyclic carrier arguments work in general, because there'll be many cases that you can't write down formulas.
So at some point, when you did the involution, the maps actually agreed on the cochain level that these squares vanish.
Yes.
And
Yeah,
you
so
can
if
see that
you
in this
had a formula that was bilinear for cup product, that was bilinear, satisfied the Leibniz rule, and was actually graded commutative on the nose, then you could take all these higher chain homotopies to be 0. The first one obviously can be 0, and then just make them all 0. And thus the Steenrod squares for that space would have to vanish, because they're defined out of any chain homotopy. In particular, if you can take it to be 0. Yeah, so there can't be such formula. Unlike differential forms, the differential forms have one advantage and one disadvantage, but they both, you see why both are related to this. The advantage is differential forms are defined point-wise. So they don't have any, in the domain of definition, they're really point-wise. So they don't have any finite extent like these simplices do. So the diagonal really sits there and you can pull forms back along the diagonal.
in a way that you can't pull back simplicial cochains along the diagonal, because the diagonal isn't a subcomplex. That's the whole problem. On the other hand, differential forms are usually defined over R. There are ways to define them over Q, and these Steenrod squares are really finite order operations. They exist Z mod 2, Z mod P cohomology. There are no such operations, rational homology or infinite operations on the even interval homology that are compatible with suspension. So that's because you take a K pi, if you take a KZN and you look at cohomology of KZN between n and 2n minus 1, well, as the generating class, that's Z, everything else is torsion. So any cohomology operations you might try to write down off of this class that don't go up to twice the dimension of the class are torsion operations. So these Steenrod squares, in fact, generate all the, well, in this case, is Z2 cohomology, they generate the Z2 cohomology.
Will we see that they commute with suspensions?
You want me to prove that? I didn't get around to that. Yeah, I can show you that. Maybe I'll make a homework problem. So the hint is, you have a kind of simplicial complex, suspend it. So the simplicial complexes have to have ordered vertices, or at least partial order on the vertices, so that the vertices of any simplex are totally ordered. You need that, because if you want to talk about simplicial change, you have to know which map of delta n onto the simplex you're using. Else you start getting automorphisms, it doesn't work. So the ordered simplicial complex, now suspend it, make this vertex minus infinity and this one plus infinity. In other words, this is smaller than all the ones in here, and now do this stuff, and you'll see that it all simplifies. And the Steenrod squares can be suspended. So that's your hint.
So the difference between the simplices and forms were that you can't approximate diagonals with simplices? Is that what you said?
Yeah, if you take, I had the square on the board, that's the case of the one simplex. You take the one simplex across the one simplex, well, topologically the diagonal's in there, but it's not a subcomplex. And in fact, what this chain homotopy, well, what the Whitney formula does says, instead of the diagonal, take the bottom edge and the right side. And the flip is the left side and the top edge. So those are your Whitney formulas. One says evaluate, well anyway. Now what's the chain approximation to the diagonal? Well, I need to send this one simplex to some two chain in this space. Well, I send the one simplex to the product of it with itself. And that's the homotopy between this and that. That's the best you can do. Whereas if I'm using differential forms, it's none of this combinatorial structure. You just pull the form back. Yeah.
What's the picture of H2?
What's the picture of H2?
So the picture of H1 is the
Well, there is no H2 there.
No.
So H always, so the highest H you can have on a P simplex is HP. And HP of a P simplex assigns the product of the simplex with itself. Remember the acyclic carriers. This thing has to be in the image of a simplex, of a delta n, has to be in delta n cross delta n. So the biggest cell you have there is 2n cell. And this, my statement about square naught is the identity, is the statement that you associate to sigma, sigma cross sigma. Because if you evaluate sigma on the first face and sigma on the last, if you evaluate alpha on sigma times alpha on sigma, you seem to get alpha on sigma squared. But we're going to work on it too.
So the picture is four-dimensional.
Yeah, so you need a two simplex, you need a surface across the surface, and you have two simplex across two simplex, and you get some H2. Yeah, why don't you work it out? Okay. So next week, I'll start on
simplicial sets. The week after that, I'm not going to be here, but I thought, I gave a lecture recently in, where was I? Oxford. And we'll try to get, it was tape, so I'll try to get a copy of the tape. It's about Ricci flow and the proof of the Poincare conjecture. This is a clay math 20th year celebration. So I got to stand up there and talk about the one of the 7 problems that they had solved. So I needled the algebraists and said, come on guys, get moving. So if I can get that displayed here, I'll ask Pat. Then I'll do that 2 weeks from now. If not, I'll cancel class 2 weeks from now. We meet next week, right? There's no vacation. Columbia has vacation next week. Election day. Remember back in the 60s when the students wanted to, they protested that they needed time off to go politic? Well, there's still 2 days left to go. Maybe the election day. Yeah, I guess the state doesn't let its employees or students go off in politics.
It's true though, in civilized countries, they vote on Sunday.
Yeah, I'll switch it.